Okay, so welcome everyone to the 13th lecture of this year's Internet Seminar. It's been a while that I appeared here on stage. Hope you all recall that my name is Moritz. What else funny should I say in the beginning? Well, initially I wanted to say that I tried to grow my hair to look like Robert, but Robert is not going to the hairdresser, so he's still ahead of me. But anyway, back to serious topic. We are going to do one more thing in this Internet Seminar, and this is we're going to solve the Kato conjecture. More precisely, Kato conjecture has been solved in 2001 or 2, depending on whether you look at the paper or when the proof was written. And I'm going to present, using all of the material from the lecture notes so far, I'm going to present to you over the next 2 weeks the solution of this conjecture. Okay, so you may ask, why do we all do all of the material and in the end we're just using it to prove one result? Okay, this is partly because I love the Kato conjecture and I love all the technique that's behind it, but the Kato conjecture is not the primary focus of these lectures. The focus of these lectures, as the title of the ISM says, is about harmonic analysis techniques for elliptic operators. Okay, and the Kato conjecture and its proof is just a beautiful showcase where you see how all of the different branches of math centered around elliptic operators in divergence form can be put together, and each of the different things that we've seen, so that is functional calculus starting from Laplacian, then going to sectorial operators, then it's Sobolev spaces using maximal operators and Riesz potentials. We're going to have Carlson measures and quadratic estimates, and then we're going to put a little bit of really hard harmonic analysis into the mixture, and then we all steer it and it gives one compound, and this compound is going to be the proof of the Kato conjecture. So for me, and what I'm trying to transmit to you guys, is that the Kato conjecture is there to show you how can all use different tools to solve one problem that is easy to state but requires a lot of work from different areas. And that's probably why it took so long to solve this conjecture. So I think Robert at the beginning of lecture 12 showed you a little bit the background of the Kato conjecture. In the lecture notes you have seen these beautiful graphics that I did with my daughter on Christmas because she didn't want to go to sleep and we had to do something that's really tiring, so we did LaTeX graphics. No joke. And and then Sylvie in the last lecture, second part of lecture 12, talked you through the approach to proving the Kato conjecture, right? Because if you look at it, it says I have to identify the domain of the square root of the operator. I cannot compute it just simply like for the Laplacian using Fourier transform. So if you see that for the first time, it's probably like me seeing it for the first time many years ago. I thought how are you even going to approach the problem in the first place? Right? And what Sylvie showed to you is that the Kato conjecture can be reduced to proving a square function estimate. And in the following lectures, and also today, there's going to be a lot of square functions estimates, so I'm going to call them SFE, square function estimate. And the particular square function estimate that you had to prove to solve the Kato conjecture is the following. So it's a square function, meaning there's a quadratic integral, some quantity is squared, and you integrate dt over t. And the precise quantity here is TL times t squared L to the minus 1 of u. You take L2 norms on Rn, you square that, you integrate dt over t, and you seek control by an L2 norm. Now this looks a lot like the quadratic estimates for McIntosh's theorem from lecture 8, but the complication in this thing is that the scaling is not correct because there's a TL here, but the scaling goes with t squared L, and also the bound is not in terms of u, but it should be in terms of the gradient of u. Okay, and the gradient of u sitting on the right hand side is somehow an artifact of the Kato conjecture itself, comparing functional calculus of L with the gradient, which is not part of the functional calculus of L, it's just the gradient. Okay, and then this should be squared. Okay, so that's the thing that you want to prove. And so some notation I'm going to fix once and for all. It's going to apply to today's lecture. It's going to apply to the second part of lecture 13, and it's also going to apply to next week. It's not horrible notation, just keep it in mind, okay? So L is always going to be a divergence form operator on Rn, of course, and then it has ellipticity constants lambda and capital lambda going to associate to this guy. Keep in mind that we have to prove this estimate for every operator L, which is fine because we're not going to specify the coefficients anywhere other than using ellipticity. Okay, then sometimes I'm going to use constants C and C. These are always positive constants in my estimates, and they should depend only on dimension and ellipticity. Okay, so whenever I write a statement with a capital C or C, there's going to be one of these constants. For example, the constants that appear in off-diagonal estimates you've seen in lecture 11. Okay, and then I'm going to ease notation a little bit. So instead of writing L2 norms on Rn like this, I'm just going to write it with a 2. Okay, because we're going to have a lot of these norms. In particular, this will just be norm 2. And then I use the same notation for tuples of functions. Okay, so also this is going to be just a 2 in the notation. And so the same for tuples, say f. Typically, capital F is going to be one of these vector valued functions. I mean, vector valued in a very easy way. It's just finite number of components. Components I'm going to write with indices, and these are functions in L2 Rn to the n. All right, it's no big deal. It's just that I have said it once, and I'm going to remove it from the notation when it doesn't matter. All right, so, you know, when you look at this square function estimate, I think it's equation 13.1 in the lecture notes. I mean, just from the aesthetic point of view, I think there's something that is disturbing me in this estimate. And what is disturbing me in this estimate is that there's a gradient of u sitting on the right-hand side, but there's no gradient on the left-hand side. Right, so I want to view this thing, if you think about it, as bounding a linear operator. Right? It should be a linear operator acting on something, and you want to bound it by the function that the operator is acting on. So it would be much nicer, much more aesthetic, to actually write the left-hand side in 13.1 also in terms of the variable gradient of u. Okay, so I'm trying to write the left-hand side of 13.1 in terms of, so capital F, the gradient of u should be the variable in our estimate. And it will be look much more pleasing. So how do I do that? Well, the thing that you have is TL applied to the resolvent acting on u, and now I cannot just commute the operator through like this, right? But if I use, instead of the L, I use the curly L, that is the divergence form operator, not as an operator in L2, but the bounded guy mapping h1 to h to the minus 1. These guys and the resolvents, they are the respective restriction using the curly notation. So I can replace this L by curly L. And once I have the curly L, well, u is in h1. So I can put the curly L through. So I can write it as t 1 plus t squared curly L inverse applied to curly L of u. And then curly L you've seen in lecture 11. Curly L is a compound operator using 3 components: very weak divergence, multiplication by a, weak gradient. Okay, so I'm going to write it exactly like this. I'm going to write it as t 1 plus t squared L to the minus 1. Divergence, I'm going to put a minus sign here because it's minus divergence, A acting on gradient of u. Right? It's the same thing. And then this guy here, I'm going to call capital theta t. Okay, and then this is the operator I should be working with. So definition, I just said equal capital theta t of f is going to be minus t, it's going to be, t squared curly L inverse diff a f. Right, that's my notation. And if I use that notation and I go over here, then using f as this gradient field, the right hand side is f and the left hand side of my quadratic estimate is theta t acting on f. Okay? And so it's about proving an estimate for these theta t operators acting on vector valued functions capital F, and if necessary at points we can assume that we only need it for gradient fields. Alright, so what do we know about this operator? Well, you see, if the A wasn't there, then this would be just this divergence family you've seen in lecture 11, the dual of the gradients of the resolvents. And so that would be bounded on L2 uniformly, and it would even satisfy L2 off-diagonal estimates. Now this multiplication by A doesn't change anything. It's bounded on L2. So boundedness on L2 uniformly in T is automatic for these operators. And also multiplication is pointwise multiplication by a matrix. So if I know the support of F, the support of AF is not going to be larger. Right? So it also doesn't enlarge the support. So my conclusion from that is following remark, this theta t family, T positive, satisfies L2 off diagonal estimates by corollary, and this I have to look up which one it is corollary 11.11. Okay, you agree? Okay, then you see very naturally I have to study vector valued. I mean baby vector valued because it's c to the n valued, but still it's not scalar valued, and it's going to matter a lot. That is not scalar valued in lecture 14 in particular. Okay, so I have to work with these vector valued L2 functions. I have many operators that I have defined only on scalar valued functions, but I can apply them in this c to the n valued setting just component wise. Okay, so that's an agreement. I'm going to apply operators on L2 Rn component wise to c to the n valued functions. Okay? For example, something like resolvent of a Laplacian, if I apply it to tuple functions like this f, I just apply it to all of the fj and then I merge them together in a vector. It's just as easy as that. Okay, so, well, now we know what we have to prove. So the question is, how do we prove it? Right? And I'm not only have to tell you how you prove it, I should also tell you where all these ideas come from. Right? Because you want to learn something about things outside of the Kato problem. And so we decided to give you a little historic account explaining at the same time the strategy for proving all of this stuff. And so this 13.1 is called About Square Functions and Carlson Measures. All right. So, historically it starts with things that are called T1 and TB theorems for square functions. Okay, I'm going to tell you a little bit more. Well, I tell you nothing about the terminology actually today, but I'm going to teach you a second history lesson next week, and I'm going to explain to you the terminology why these guys are called T1 and TB theorem. As of now, it's just a theorem. Okay, and I'm going to explain to you what the theorem says, not why it's called like this. So these T1 and TB theorems, they appeared in the work of Michael Christ and Jean-Lin Journet in 87, and then this was T1, and then TB was Stephen Semmes in 1990. Okay, and for you, just think of these theorems as criteria to prove square function estimates of the following form. So these guys looked at estimates that look exactly like what we're trying to do. So there's going to be a capital theta of f 2 norm squared dt over t controlled by f L2 norm squared. Okay, and the estimate should be true for all f in L2 on Rn, say. Okay, so at first sight it looks precisely like what we're trying to do. Now, in these criteria, there's some obstructions that are going to make it impossible to apply these theorems off the shelf to the operator that we're trying to bound. Okay, so first of all, this is a scalar function. Okay, well, I wrote it still with a capital F because I want to show you the analogy. But f is a scalar function, and then these theta t's, they are integral operators with reasonably good kernels. Okay, I guess every one of you has seen an integral operator once in their life. I'm not going to tell you anything about it, just leave it to your imagination. Just think of your favorite integral operator, and that's all you need to follow what I'm trying to explain to you next. Okay, these are nice operators, but still it's a hard theorem. Okay, and so the story in their approach, it starts by introducing something that is called the principal part. Of theta. Okay, and the principal part is something very easy. It's just a function, and this function I'm going to call little gamma t, and it's just obtained by applying the operator theta to the constant 1 function. Okay, so constant 1 function means characteristic function of Rn. Okay, and because it's an integral operator, you can imagine that you can put a constant in there and then something comes out. And that gives you 1 function. Okay, and why is this principal part interesting in the story? The principal part is interesting because in their setting, I mean, it might be, even in this nicer setting, that this estimate fails, and they're trying to characterize when the estimate holds. And while this estimate turned out to be not always true, there was still an auxiliary estimate using this principal part that turned out to be always true. And this is called the principal part approximation. Okay? And the principal part approximation says that the following square function estimate is always true, always in their setting. Namely, I can take an integral from 0 to infinity, and then I'm going to take theta t of f, but I'm going to subtract off something, and this something is, what I do with the function is, instead of applying theta t directly, at each scale t, I'm going to average it. So at scale t, I'm going to obtain a function that is constant on every dyadic cube of generation t. So it's like a discretization if you want. This is what the dyadic averaging operator A of t from lecture 9 is going to do to us. And then at every scale, I'm approximating theta t of f by a multiplication operator acting on the dyadic averages of f, and the multiplying function in this approximation is just this principal part. Okay? So multiplication operator acting on the dyadic averages of f, and this, I mean, you can, if you just imagine very wildly all these words I'm saying, it sounds like this could be a way of approximating theta t of f. And indeed, it's a sound approximation of theta t of f in the sense that they are close in square function norm. Okay, so this estimate here is always true. Okay, so in the notation in the lecture notes, I'm gonna call this definition here, just wrap up, this is 13.2. The thing I want to prove in the SEMS Chris-Journet context is 13.3, and the principal approximation is 13.4. All right, so this is always true. It turns then out that I can somehow write this here in a different way, right? Because I want to characterize the validity of this estimate, but this estimate is always true, so I can just do stupid triangle inequality, add and subtract this thing here, and I see that instead of proving this estimate, I may equivalently replace theta t of f by gamma t at of f. Because the difference between the difference between this estimate and this estimate and this estimate is always true. And so this means that 13.3 is equivalent to the estimate where I replaced the operator theta t by the multiplication operator acting on the dyadic averages at scale t. And for this guy, I write out the L2 norm in space, because it's a multiplication operator. Sometimes one sees more when one just writes out the norm using an integral. So I write it as an integral from 0 to infinity, and then the L2 norm in space I write out. This is integration on Rn, and then this is going to be a of t at x squared times gamma t. Well, you see, this is just a product of two functions. I forgot the f. So it's the product of this function squared times gamma t x squared dx dt over t. The only thing I did is just I wrote it as two absolute values squared, which is okay, it's a product. And the reason why I want to write it like this is that this here I want to view as a measure. This guy here defines the integration with respect to my Borel measure d nu of xt. And I want to do that because not only now I have seen that 13.3 is equivalent, thanks to the principal part approximation, to this estimate, but also this estimate, as opposed to this one, this guy lives on common ground for us, right? Because we have characterized already when such an estimate holds. You remember? So what does the measure have to satisfy? It's also on the board. Has to be a Carlson measure, right? That's theorem 919. Well, 919 said that it's sufficient to prove that it's a Carlson measure estimate, which is anyway the direction we want to go, but preceding the discussion, we also checked that it's necessary. Okay, so it's really an equivalence. And so I have to prove that gamma tx squared dx dt over t is a Carlson measure. All right. So that's it. That's the idea. Square function estimate is equivalent to checking Carlson measure condition for the principal part. Now, all of this is going to be wrong when I try to apply it to this operator. First obstruction is that it's scalar valued. Second obstruction, and that's the really severe one, is that our thetas over there, there's absolutely no reason to believe that they are good integral operators. But nonetheless, and that's when really the proof of the Kato conjecture in all dimensions picked up speed. There was work of Aucher and Chamitian in the end of the 90s, where they sort of started developing this kind of reduction inspired by Sem's result in the context of our operator. Okay? And so the goal of episode 13 is I want to do the reduction to a Carlson estimate in the setting of my square function over there. That is, I want to prove the principal part approximation 13.4 for our theta. Okay? That's the strategy for this week. And then next week, la grande finale is about proving the Carlson measure estimate. So do you have questions? Okay. So we're ready to go. Let's see. So I should open a new section. 13.2. I call it the principal part. So let's see. I want to prove this, so I should define this first, right? The question is, what is this? And now I see immediately two obstructions. Two big obstacles, potentially. You have to help me. I tell you the second one if you tell me the first one. So gamma of t was theta of t applied to the one function. Now, which function should I take? Should I take the one function? Should I write 1 in every component of my function? Because theta t is acting on vector-valued functions. I mean, what your long-term knowledge about linear algebra should tell you is that if there's a 1 here, this is probably referring to the basis of the underlying vector space, C, and it should not be generalized by putting just a bunch of 1s into one vector. Okay, it should be something related to dimension. So we should not have just one principal part, but we should have dimension many principal parts. Okay, so for me the first obstruction is that f grad u in 13.1 is a c to the n vector. But as I showed you this, or as I told you already, this is no issue. We're going to have one principal part in every direction. Okay, so that's reasonable to believe. Okay, after all, it's about approximating a function by multiplication, and so it should not be just multiplication by a number, but by a vector. The second obstruction is, how do I make sense of this? What is theta t of 1? Theta t is just an operator. I told you it's an operator acting on L2, but it's L2 of Rn, so there's no way of applying it to constants a priori. But So, ej are going to be the unit vectors. This is what I put here. So theta of t not defined on constants. How do I solve that issue? On this you know. Why can I apply my operator theta t to constants even though it's just a bounded operator on L2 in the beginning? You seem to know it. Yeah, you. Yes? It satisfies off-diagonal estimates, says one of the 95 attendees in the lecture hall. You're absolutely right. That's okay. Okay, by off-diagonal estimates. Okay. Thanks. So, I can I do hope that I have the thing to ever get that thing back. Yes. Okay, I put it slightly down. Of course, I'm able to jump that high, but I don't want to show you. So here's the definition of the principal part. That should be now, where are we? 13.4. Definition. So my principal part is going to be a vector function, and I'm going to define it like this. So for t positive, I'm going to set gamma of t to be theta t applied to ej. Ej are my unit vectors, standard unit vectors in c to the n, and I'm going to identify them with a constant function that takes this value constantly to ease notation a little bit. And so theta of t is going to be a vector valued function. This guy, and we know that because of off-diagonal estimates, I can define this. Theta of t has a well-defined action on L infinity, and it gives back locally square integrable functions. So this is a function in L2 log Rn to the n. Okay. Off-diagonal estimates, if you want the reference, this was definition 1114. Okay, and definition 1114 is what I'm using to make sense of this object. Now I want to work with this object. Okay, and you can imagine from the things that I told you that I'm not going to work with this object by just doing stupid L2 estimates. Okay? This is also something I want to tell you at this point, right? Most of the analysis was very soft in the way that we just took global L2 norms and we just estimated L2 norms. But now we have to really look into what this function is doing here as opposed to here and here and here. Okay, so I have to know this function in a way that is much more accurate than just computing a global norm. And so I need a formula for this. You have a question? Okay, so he was asking about the definition of the principal part. So what I'm doing is I fix one of the unit vectors. I view the unit vector as a bounded function. And then I can apply the operator theta t to this constant function. And that gives me back a function. It's a locally square integrable function. And then I'm going to do that for all directions. And I put them together in a vector. So it's a vector of functions. Yes, so this is, so ej is standard unit vector, and I ease notation by identifying ej with a function that is constantly the value ej on Rn. Okay, so it's the action on constant functions. It's a generalization of the above. That clarifies, I think. Okay. What I like about your question, it was completely natural, is that you have no intuition of what whatsoever this object is doing. Okay? But I told you we have to learn, get to know this object in much more detail than just computing a norm. And so we need a formula to work with this guy. And now here is a formula to compute it. I'm first going to compute it only on a cube, dyadic cube, that is of the same generation as the t in the definition. Okay, so I'm going to compute the principal part on this cube. Well, I'm not going to compute the principal part. What I should actually compute would be the product, gamma t times ATF. Okay, so I'm going to need a formula for potential approximants in 13.4. Okay, so in 13.4 I want to prove this. I don't have to know gamma t everywhere, I just have to know what it does on this averaged scale t version of f. So gamma t times AT of f. I want to compute that on the cube. Okay? So first of all, this is a dot product because it's a c to the n vector, and this is also c to the n vector. It's the average of f, but f is vector valued, so I average it in every component. Okay, so I should compute this scalar product, this dot product here. It's without a complex conjugation. It's just component multiplication, so it means the sum j from 1 to n over the jth component of the principal part, which is this, times the jth component of the average. Well, the jth component of the average, because I applied component-wise, is just the average string operator acting on fj. And if I work on this cube and I average at generation t, I'm going to pick this cube all the time. So this is just the average of fj on q. That's the definition, component-wise. Now this is a number, and so I can put it inside of this linear operator, and then I see that this is the same as writing j is equal 1 to n of theta t, it's theta t of, I want to sneak it in, but I also can sneak the sum in, and I want to do that probably in one step. So theta of t is the sum j1 to n of ej times fjq, right? This guy goes in, and then it becomes precisely this. All right, and now what is this quantity here? This quantity here is, well, it's a vector. The jth component of the vector is the average of the jth components, so this is nothing else but the one function times the average of f on q. So that's what this composition looks like. And so I can continue, right? I write it as theta of t times the one function times the vector valued average of f. And now this here, I view it as an L infinity function. And so I can go back to the definition, how I extend it by means of off-diagonal estimate, the action of operators from L2 to L infinity. You remember that I could fix a reference ball, and then I had to take a limit of radii going to infinity. So this was definition 1114. It says I should put the limit as k goes to infinity of theta of t times the indicator function of 2 to the k b times f of q, f average q. This was precisely how I defined extending this function here, extending the action of theta of t to this function. And I had a freedom in this definition because it did not depend on the choice of b. B could be a ball, it could be a cube, and it could be any ball or any cube. Now guess what, which cube or ball I'm going to take to make the computation easy. Of course, I'm taking the same cube where I'm trying to compute the product. Okay, so I replace this b, I take b just as q. And then I'm gonna split, as we always do, everything into dyadic annually. So I'm gonna write this as the sum going from L is equal to 0 to k to the minus 1 of theta t times indicator function of the Lth annually around q times fq. Because this is the region where the rate where you're between q times 2 to the L plus 1 and q times 2 to the L. So you stack up these annually, cluck, 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 cluck. It's going to be a ball, and the ball is going to be 2 to the k. Okay, so drawing is like this. You have your little q, and then you do this annually decomposition, and so on and so forth. And so instead of taking the indicator function on this huge cube, so this is 2 to the k q, and then you have these averages stacked. So the whole thing here, I should say, the whole thing is 2 to the k q. And then this first annulus here, this is c k minus 1 of q, and then these annually, they become smaller, and in the middle there's q. Okay, and then you stack, and you get that. Agreed? And so now this is a limit k going to infinity of a series that we know that is convergent. So, okay, and that's a formula. That's a formula for this object is equal to this infinite series. Okay, and this, if I want to apply any kind of mathematics in the setting of the internet seminar to this sum, then I should probably use off-diagonal estimates, because I'm sitting on a cube q and I'm measuring theta of t very far away potentially from the same cube. Okay, so here I'm going to use off-diagonal estimates. So that's inevitable. Has to be like this. Now you tell me at this point if I should re-explain one step in this computation, because then for the rest of the lecture I'm going to work with this formula. Okay, I'm going to call it a name. This is 13.6. Okay. I think the most confusing thing, if you see it for the first time, is just when this guy becomes this guy, but this is really just splitting the vector valued average into the components. It looks horrible, but it's very easy. Now, if I want to use off-diagonal estimates, then let me do a short recap on what is possible in this context. Well, if you apply off-diagonal estimates here, then the natural term that we always going to see is that I have in the exponential, I'm going to have the distance of the Lth annulus around q in comparison to q, because q is where this formula is valid in the first place. And then because it's theta t that I'm applying, I will be dividing this expression by at. And this is going to be popping up in the exponential function with a negative sign. Right, so if I want to estimate, I need a lower bound for this. Now, what is a lower bound for this? This goes like 2 to the L, because this annulus leaves out 2 to the LQ. So it goes like 2 to the L minus 1 times the side length of Q. And at the case, at the at the tth generation of dyadic cubes, the side length of Q is going to be larger than T. And so if you measure distance, this is, you see it here, this is like half the side length of the Q, so it's going to be T over 2. This is the formula that everyone wants. You've seen it when Robert told you about it the first time. The issue with this is when you set L is equal to 1, then the distance is 0, but this function here is not giving 0. but we can just slightly correct it, and we put a -2 here, and then we're on the safe side. Then it also is correct for L is equal to 1. Okay, and then you just simplify. You can cross out the t like this, and the 2 you're going to put downstairs. Okay, so it's going to be 2L minus 2 over 2. So whenever I apply off-diagonal estimates in this context, this term here is the important one because it's going to pop up in the exponential term. Okay, let's do one computation with it, then we make a break, we digest what we've seen, and we go on to the more serious stuff. Okay, so I showed you a formula how to compute this potential approximation in my principal part approximation. Now I'm going to show you a little lemma. That says that these approximants are uniformly bounded in L2. That's absolutely necessary because the theta t's, they're uniformly bounded. So in addition to all other things, I should have uniform bounds for gamma t at. And the lemma says nothing else but this. So gamma t times at of f in L2 norm is bounded by one of these allowable constants times f in L2 norm, and this works whenever t is positive, and f is in L2 of Rn to the n. Okay, so the potential approximants are uniformly bounded. Doesn't say anything about whether they approximate in any reasonable sense the operator theta t, but at least it's a uniform bound. And so I want to control these operators. Yeah, so how do I do that? I claim that it is enough to work cube by cube. Okay, so which equation is that? That should be 13.7 then. I claim it's enough to prove that for every cube dyadic of generation t, I can bound gamma t times atf in L2 norm on Q by the same constant f L2 of Q. I claim if I have this, I'm done. Now why is this? Well, imagine I square both sides, then here I'm integrating the function squared over Q, here I'm integrating f squared over Q. Now I sum up over all Q, then the sum on the left hand side is going to produce the global norm, and likewise the sum on the right hand side is going to produce the global norm. Cubes are non-overlapping. So this implies this. Okay, so make a check mark here. We convinced ourselves that this is enough. Alright, so now I have to estimate gamma t at times f on a cube, and so I can use this formula. Alright, so now gamma t times at f in L2 norm on Q is the L2 norm on Q of this expression, which is the same thing as the L2 norm on Q of this infinite series, and I'm just using triangle inequality to put the L2 norm inside. So by 13.6, my calculation over there, this is bounded by the sum L from 0 to infinity of theta t acting on 1 CLQ times FQ L2 norm Q. Just took the triangle inequality in my formula. And now that, of course, is no problem at all for the mighty off-diagonal estimates. The function is supported in an ELIDAS. I'm measuring L2 norm on the cube, so I use off-diagonal estimates. and I can bound it by constant times exponential of minus exactly this expression times a constant. So it's minus c times the distance, and the distance I'm already estimating like this, so it's 2L minus 2 over 2. And then I get f average the constant function on L2 CLQ. Okay, that's off diagonal estimates, that's how they work. Now, in this calculation, there are a lot of terms that are superfluous. And I'm going to show you once how I massage this term a little bit to look nicer. And then when I do it next time, you know the massaging and you do it just in your head on your own. Okay, so massaging goes like this. I absolutely don't care about what the values are as long as these are positive constant that don't depend on anything but ellipticity and dimension. So instead of the 2 here, I can erase the 2 and just put it, maybe, I can erase the 2 by just replacing c by c over 2. And I can also erase the minus 2 here because it gives e to the small c times 2. Well, that just goes into the constant here. Okay, so this one I can also erase by changing the value of the constant. So in the end, I have just constant times e to the minus constant times 2 to the L. That's what I have. Right, so that's the sum. Now this sum has to be computed. So I have to compute the L2 norm on the right-hand side. Well, this is the L2 norm of a constant function. So that's easy to compute. This just gives you the measure of the region that you're integrating to the power 1/2 times the value of the constant that you're having inside. Okay, so then I'm putting the average out and I'm dividing by Q, which is the same thing. And I use Hölder on this F because F is something I want to measure in L2 norm, not in L1 norm. So if I do Hölder, then I'm getting F L2 of Q. The price I have to pay is the measure of Q to the power 1/2. So that gives me, instead of full measure of Q, this gives me measure of Q 1/2. And it gives me measure of CLQ outside. Okay, and so now you have to wonder how large is this measure? Well, the measure of CLQ is smaller than the measure of Q blown up by a factor of 2 to the L plus 1. Okay, so that blows up measure by 2 to the L plus 1 times n. So this constant here is bounded by 2 to the L plus 1 times n, and there's one square root outside, so it's n over 2. Oh, it's bounded by this, right? Because I bound the annulus by the larger ball. I bound the measure of this guy, this orange region here. I bound it by the measure of the full red cube. Okay, so now let's take my favorite color, purple, and see what we have. If I have this estimate, there's an L2 norm on the right-hand side, which is good in view of the thing I want to prove here. So I take this estimate, and I throw it back in there. Then it gives me L2 norm times a series. In the series, there's e to the minus c to the 2 to the L times this polynomial factor. So the series is converging. So this estimate here goes back here, and you get the claim, and the proof is done. Okay, let's make short break, and then we're going to continue by showing how these gamma t ATs actually approximate the theta t. I resume at 45. All right, are you guys back? Back with me? Blackboard has tried, so let's continue. I erased every result from the first part because I need space. Okay, but so far what you've seen is that we should be interested in the principal part, in scalar multiplication with the diaretic averaging operator, and these gamma t AT things, they turned out to be uniformly bounded in L2. So my next step, if you think of what the principal part approximation was, my next step should be to prove that gamma t AT approximates in any reasonable sense theta of t. Okay, and this is the next lemma I want to prove. So 13.6 lemma is the first approximation result, just the first result ever in this course that compares theta of t with gamma t AT. Okay, yeah, I want to write it like this. So it's gamma t AT applied to f. And if I measure this in L2, it turns out that I can bound it by c times t times the gradient of f in L2, and this works whenever f is vector field having components in H1. So this here is like a n squared vector, but it's the component y is L2 norm. Okay, so this is an approximation result. It at least shows you that it's a good approximation when t is small. I'm going to comment on this later. All right, so how should we prove this? We have two formulas, right? I now have to remember the number of the formula because I erased it. Okay, so recall 13.16. If I work on a cube, okay, I should say first I do the step proof in two steps. Step one is I'm going to work on a fixed cube. Okay, I'm going to do something on a fixed cube, and then I'm using some off-diagonal magic to prove a global bound. Okay, so on a fixed cube, I have two things. I have 13.6, that was my computation here, that showed you that gamma t times AT f is equal to an infinite series of theta of t times in annually localized versions of the constant average of f. Okay, and I have another formula, so this allows me to compute this. I can also compute theta of tf, because theta of tf is a bounded operator L2. L2 function I can also split into annulus components, and so this is the same as series from L is equal to 0 to infinity theta of t times f. Because if I would leave that out, if I cross out the theta t on both sides, then it's just L2 convergence by dominated convergence, and then theta t is a bounded operator. Go like this. Or you say, well, the extension by off-diagonal estimates was consistent with the L2 theory. Okay, so I take the difference of these two formula, and I can bound theta t minus gamma t AT applied on f. I bound it in L2 of Q by, well, I take this series minus this series, and then I use the triangle inequality. So it gives me sum from 0 to infinity theta of t applied to localized version of f minus its average. L2Q. You agree? And now you get a first feeling of what's going on, because now the comparison on the operator level has all of a sudden moved inside of the operator by computing f with its average on cubes. So you begin to believe that at least when the cubes are small, that shouldn't be too bad as an approximation. Alright, so of course I use off-diagonal estimates because I'm localized in an annulus and I'm on a cube. And of course I'm going to use the massaged one as I told you before the break. So I'm just writing L is equal to 0 to infinity. The constant C in front I just ditch in the notation, and then it's going to give me e to the minus c to the 2l times the norm of f minus its average on the annulus in L2 normal. Right? Off-diagonal estimates. Now I want to control that. And I already told you how I control it. I'll control it using the gradient of f. So now there should be alert Poincare-Sobolev in your head. Right? Estimating f minus the average by the gradient, that's Sobolev-Poincare inequality. The only thing is that Q is not a subset of this annulus, but I can be very generous in this estimate. I'm just replacing the annulus by a huge cube that contains it, 2 to the L plus 1 Q. Then the estimate is still correct, and now I have the huge cube inside sitting the small cube, so this is okay for Sobolev-Poincare. Okay, so short break in the estimate. What number was Sobolev-Poincare? Sobolev-Poincare theorem 1017. I'm going to use it, of course, with exponent 2 on both sides, and I'm going to use it because f is a vector-valued function. I use it component-wise, which is just totally fine. Okay, so Sobolev-Poincare says f minus the average on a subregion. The subregion, let me pick a color and indicate to you how notation was when I talked about Sobolev-Poincare, or Sebastian to be precise. Hi Sebastian. Not sure if you ever see this video, but that was your thing. If in the notation of Sebastian this was E, was the subset of my domain where I'm applying Sobolev-Poincare, so the subset for averaging. And then it was in L2 on 2 to the L plus 1 Q, and that thing was back then called omega. And so Sobolev-Poincare says there is a good constant C, and then I get the Sobolev-Poincare constant in here, and then there's going to be the gradient of f in L2 on omega, which is the large cube. Now just have to remember what the Sobolev-Poincare constant was. So we had to compute the diameter of omega to the power n. We had to divide by the measure of E, and then we had to multiply by the volume of omega to the power 1 over n. Okay. Just believe me, I know what I'm doing. So this is Sobolev-Poincare inequality. Okay, now we have to compute this constant, because I'm interested in particular in the dependence on the constants on t and L. So I write everything in terms of the length of the cube, and because the length of the cube is comparable to t up to multiplying dividing by 2, I can write everything in terms of t. So diameter up to a dimensional constant is going to be 2 to the L plus 1 times the length, so this is t, and this is power of n. The measure of the cube is side length to the n, so this is t to the n. The measure of this guy is, well, the measure of a cube to the power 1 over n is just the side length, so this is 2 to the L plus 1t. Okay, and the gradient stays where it is. Just stay there. And now let's move the blackboard up. you see lots of things cancel. For example, t to the n cancels this t, and then everything that is not catching an n, like 2 to the n, it just goes in the constant. So I can say this here is c times 2 to the l plus 1 n times t. Right? There's 2 to the ln, and then there's 2 to the l, gives 2 to the l plus 1 n. Good, so let's take a square around it, because this was just some intermezzo allowing us to control this guy here. So with the intermezzo at hand, I can just complete the estimate. Okay, so I get, at the end of the day, I get the quantity I started estimating is bounded by constant times t times the sum in L over over 2 to the L plus 1 n e to the minus c 2 to the L times gradient of f in L2 2 to the L plus 1 q. Okay? Nothing else but just take this estimate, throw it in here, keep track of the terms. I get that. So that's a good bound on a Q. Right? It controls the thing I want to bound globally, at least on Q. The factor t is already there. There's some off-diagonal garbage sitting here. The gradient of f is already there on a slightly larger cube. Or a very much slightly larger cube, because the L can be as large as we want. So, but that's no harm for us, because we have off-diagonal estimates. So step 2, off-diagonal estimate magic. Basically, this is a repetition of a proof that Robert showed you 2 weeks ago. I'm going to repeat the proof nonetheless, because I think it's good for you to see once again this strategy, because it's so powerful. Okay, so in principle, I have like an estimate on Q with all these tails, because for single cube I'm using information of f still globally, but all these tails are multiplied by rapidly decreasing prefactors, and we can turn it therefore into a global estimate. So how does it go? Well, I start with theta t minus gamma t times at applied to f. I take the global norm and I take the global norm squared, say. The global norm here is nothing else but the local norms that are already estimated squared, and then I sum over all cubes, because they're cubes at generation t, they're partition of r to the n. So this here becomes a huge sum indexed by dyadic cubes of generation t of the local L2 norms squared. And so the local L2 norms squared, they are the sum L to infinity 2 to the L plus 1. Oh, I forgot the n here. Sorry. Not that it mattered, but okay, I forgot it. Times gradient of f in L2 2 to the L plus 1 q, and all that squared. Okay. Let me just show you that and there's a t missing. There's a t squared missing. Okay, let me just show you that I used this part here reappeared over here, and the reason why it reappeared is because it's an upper bound for the local L2 norm on Q, and I had to square all the local L2 norms and then sum over the cubes, so I get this horrible expression. But the expression is not as horrible as you may think. So the first thing is that I can take this 2 and just throw it in there, and I can also forget about this. Okay? If you think of Robert's proof, he showed you precisely how to do it. You split this here into product of two sequences corresponding to little L2 sequences, and then you use little L2 Cauchy-Schwarz inequality. You get a numerical series that converges, and then the square is in the inside. Another way to see it is that you say, well, this is like a little L2 norm in a weighted little L2 space. The weight is this thing here. The weight has finite mass, so it's just Jensen's inequality. The convex function square goes to the inside. Okay. Either of that is fine. It's okay for you? Okay, well, if it's sitting in the inside, then I just go on with Robert's tricks. Now I want to change the order of summation, right? So I want to take, let me take green color, let me take this sum, I can throw it out. Okay, so I get the summation in L first, L from 0 to infinity, and then I get the summation in the cubes. I have these local L2 norms squared, so this is going to give me integrals of gradient f squared. I integrate on the enlarged cubes. Okay, so if I write it like this, this would be expression for this norm squared. The square went inside. And then I have the sum over all q. I can use like monotone convergence and throw the sum over q inside of the integral. So that gives me integral in q over all these generation t cubes like this. And the only thing I forgot then is the exponential factor sitting there, and then the estimate is okay. And then you see that all collapses because this summation over partitioning but enlarging the cubes by factor, you can just compute what it was, and that was one of the exercises. This is just 2 to the L plus 1 n by stupid combinatorics. And then you get c times t squared times, well, f is measured in L2 norm globally now. And the garbage summation L is equal 0 to infinity. This is going to be the sum in L over 2 to the L plus 1 times n e to the minus c2 to the L. Well, this is just a numerical constant, right? It's a convergence series as before. So I can just throw it into the constant. Okay? And then you have it. That's it. That's the global estimate. This guy squared is bounded by ct squared times the L2 norm of the gradient. Okay, so that's a result. Now for me there are two shortcomings of 13.6. Remember that the quantity that appears in 13.6 top blackboard is going to appear in a square function estimate. So I'm going to square it, and then I'm integrating over dt over t. So if I use this estimate over there, then things get better when t is small, because I have a factor of t in front. But things are even worse when t is large, and I have not proven anything reasonable when t is large. Okay, so that's the first shortcoming I want to write down. I only get decay when t goes to 0. And in this integration with respect to dt over t, I have to find a way, and no matter what, but it's indispensable to find decay when t goes to 0 and to infinity. And I just completed one half of it. But even more disturbing, I did something I do not want to do, because imagine my goal, there was a square function acting on f. And at the beginning of the lecture, I made the effort of writing everything in terms of f. And now what did I do? Me idiot, I produced an estimate with a gradient of f on the right hand side. Later on, the gradient f is going to be the gradient of u already, and I don't want to use the gradient squared, of course. Okay? So the gradient of f on the right hand side instead of f. Okay, and these are severe obstructions, questioning if the estimate is useful in the first place. Now, there is an idea, namely, I will not apply this 13.6 directly to f being the gradient of u, but I introduce additional smoothing. I'm going to show you in the remainder of this lecture how. But to a smoothed version, and this smoothed version is going to be pt of gradient u of f. I'm going to write it as q2 of u. Okay, so I'm going to introduce in a second a smoothing operator pt, something like convolution, but I do it in a very precise way. And then I hope that when I introduce this additional variable via smoothing acting on the gradient of u, and I use 13.6 for the smoothed version, then the smoothing is going to help me with the quadratic estimates. Long ago in lecture 4, you saw that our initial motivation to study quadratic estimates came from Fourier analysis and estimates involving convolution operators that smooth out the function. Okay, so to make things precise, that's 13.7. I need a definition. Let me see what time it is. Oh, that's good. Okay, maybe you have to go 5 minutes over time, but not much more. I'm going to introduce to you the smoothing operators. So for t positive, I'm going to define two operators, pt. The smoothing operator is, I could pick hardly anything, mostly anything that does the job for smoothing, but I want to do it with the resolvent of the Laplacian. And then I want to be able to say something like smoothed version of the gradient is something like applying an operator directly to u. So I set qt to be t times gradient times 1 minus t squared delta to the minus 1. Right. And so I want to play a t here. Okay, and then you see these are resolvents and gradient families associated with the divergence form operator Laplacian. So these are uniformly bounded families in L2. Just one remark. There's a commutation property that is quite useful in this context, namely that I do have indeed what I tried to tell you here. So t times pt grad of u is the same as qt of u when at least say u is in h1. Okay, and probably the easiest way to see that this is true is if you apply the Fourier transform on both sides. Okay, so when you apply the Fourier transform, either way, you're going to see that you end up with the same symbol, which is 2 to the pi I t xi times 1 plus m of xi to the minus 1 u hat of xi. And m is the function that corresponds to the resolvents of the Laplacian in the functional calculus from long ago. Right? In the end, on the Fourier side, this is a multiplication operator, this is a multiplication operator, this is a multiplication operator, and a common domain. I mean, these multiplications, they commute, of course. They have to. Okay, so we have this property. Okay, and so the next lemma summarizes what I know about these operators. And then the final step will be very easy, just assembling what we have so far. Okay, so 13.9 lemma says if I take f in L2, so I take a vector field in L2 and I take a scalar function in H1, then these Q operators, they give rise to three properties. And now this lemma will be for you a perfect opportunity to catch up with all the things you know about square function estimates, Kato for self-adjoint operators, and the Cauldron reproducing formula, because we're going to use it all at once. Okay, so there are three things. There is a square function estimate. The square function estimate says that I can build a controlled square function out of Q of t. So Q of tu squared dt over t, this I can control, or by f, sorry. This I can control by f. Okay, so the Q of t, guys, they give rise to a L2 bounded square function. There's a joint square function estimate, which says that I can do the same thing for the qt star, guys, but here I have to be careful, and I should probably pick a vector field that is a gradient field, and then it works. Okay, so that's this thing, and then the third thing is there's a reproducing formula using qt, and it's a joint, and it goes like this. So you have the integral from 0 to infinity, and then I take 2 times qt star, and this gives a reproducing formula on gradient fields. Okay, that's the lemma. Now all of these things, they should look very familiar to you, because this is a square function estimate involving something like functional calculus. This as well. This looks like a Cauldron reproducing formula. The only thing is that these formulas do not happen entirely inside of the functional calculus for the Laplacian, because we also use gradients. Okay, they are just ever so slightly off the setting that is purely operator theoretic, because there is the gradient. But you know that because Laplacian self-adjoint operator, or because you followed lecture 4, that we can deal on the level of global norms, like here, we can always deal a gradient for square root of the Laplacian, and then we're inside of functional calculus. Okay, so I'm going to just show you how that works to convince you that these things, they work. Before I start the proof, let me just say I have to use things like this because the Kato conjecture in the first place is about comparing functional calculus with something that happens out of functional calculus for the operator L, namely the gradient. Okay, and so in the baby version, we see it here that we're going to need formulas that use functional calculus for Laplacian, but also gradients. So it's, in the grand scheme of things, it's very natural that we have to encounter estimates like this. All of them are going to be 3-line proofs. Trust me. There's lots of space. Qt of f in L2 norm, I take the definition of Qt, which is up there, is t times gradient times resolvent of the Laplacian, applied component-wise. But now I have the Kato property. Kato property 412, red color. 412 says, instead of taking the gradient, I can take the square root of the Laplacian. So instead of taking t times gradient, I can deal this for minus t squared Laplacian square root. And then you see, I want to prove quadratic estimates for this. Well, this is something like auxiliary function in the functional calculus. Is square root times 1 plus z to the minus 1. Okay, and so the square function estimate from this now follows from quadratic estimates for Laplacian. So claim follows by quadratic estimates for minus delta with the function f being square root of z times 1 plus z to the minus 1. Okay, and quadratic estimates for the Laplacian, something that we did. See, so we went back to the functional calculus of Laplacian, and it was easy because we have all the material. So if I want to do the adjoint formula, I use Lemma 11.10 in order to be able to compute the adjoint. And the lemma says the adjoint is given by the gradient family. So it's minus t times 1 plus 1 minus t squared delta minus 1 divergence. This is the formula for the adjoint. And all of this is acting on the gradient of u. Okay? Allow me, please, to be sloppy in the sense that for the Laplacian, I'm not introducing a curly Laplacian like I did for the L. Okay? So this is a curly Laplacian if you want, because there's a divergence. Well, divergence of gradient gives me back Laplacian. So this is nothing else but minus t delta 1 minus t squared delta to the minus 1 applied to u. And now this, for this guy, we have to do a square function estimate. But in the shape of an operator L, this resembles TL 1 plus t squared L to the minus 1. So for the operator L, this is precisely the square function estimate I want to prove. This is where I started this morning from. But for the Laplacian, I already know the Kato property. And the square function estimate is equivalent to the Kato property. This is why we're using the square function to approach Kato. But since for this operator I already know Kato, I can use the reduction of Sylvie backwards. And so the square function of this is controlled by Kato property, and the results from 12.7. Okay, so claim by Kato for Laplacian and 12.7 backwards. Says that this square function here is controlled by the gradient of u, which is precisely what I'm claiming over there. Okay, so it remains to prove the C part. Now in the C part, I'm giving this thing here a number. So this was supposed to be what? 1312. So I'll apply 1312, apply qt to 1312, because in the reproducing formula I want to have qt star grad of u. Qt star grad of u I already know how to compute. I just apply a gradient and a resolvent. Now, similarly to what I've shown you up there, I can switch to Fourier, and I see that I can compute any object in the calculation as I want. So the q of t is going to introduce an additional gradient, an additional resolvent, and using the Fourier transform I can place the additional gradient and the additional resolvent at a spot of my choice. So I take this formula, I need to introduce on the right hand side a t, a gradient and a resolvent. And so how am I going to do it? The t squared delta I leave as it is. The additional resolvent I have to introduce, I introduce here to make this a resolvent squared. And the additional gradient I have to introduce, I introduce it at the very right, because then this is grad of u. Okay? And so it should be read in this way. It's this operator acting on grad of u. Now I want to reproduce this element of L2 by this sort of formula. But this here is just an auxiliary function. This is f of minus t squared delta, with f being the function z times 1 plus c to the minus 2. So it's a beautiful h0 infinity function. I can use the Calderon reproducing formula. And it says I can reproduce the things. And you can compute the normalization factor, then you find the 2. Okay, so claim by Calderon reproducing formula. So once again, you see, if I apply this qt star guide to a gradient field, I can view it as something happening entirely inside of the functional calculus applied to the same gradient field. But I used the gradient field structure to do that. And actually, you could check that this reproducing formula is not going to work if you are not a gradient field. But that's a different story, and we don't need it. All right, so I guess my time is over. Yeah, but I don't want to send you home like this. I want to write down one result that requires a one-line proof, and it's going to be the perfect summary to end the Monday lecture, because we have done, in a way, half of the distance towards the principal path approximation. Okay, so let's wrap up. This is going to be which result? 1310. 1310, I call it a smoothed principal path approximation. It's going to be our principal path approximation, but with a smoothing operator. And it says the following thing: integral from 0 to infinity theta of t minus gamma t times at applied to f squared dt over t is controlled by f in L2. And actually this thing doesn't require a gradient field. It's going to work for every L2 function. Okay, now you say stop, because if I would be able to prove this, then this would also already be the principal path approximation. Okay, and then we could have a beer on Wednesday instead of having a lecture. But things are not as easy as they are, or as we hope them to be. The word smoothed refers to the fact that it works with an additional PT. And so next lecture I have to get rid of the PT. But let's just, for today, see that with a PT it works. Don't worry, it's a one-line proof. I look at the function inside of my square function. I apply the lemma. The lemma, which number was it? The one that we have up there, 13.6. 13.6 is going to give me constant times t times the gradient of whatever I put here. And whatever I put here is a pt f. But t times gradient times ptf is just qt. So this is qtf. But for qtf, I have a square function estimate by f, which is exactly here. So that's it. Proof complete. Thanks for listening today, and hope to see you on Wednesday.